Okay, this is another sample ice problem, one in which we have to carry it out a little bit differently from the one I showed you earlier. So we have a 1 liter flask filled with 1 mole H2, 2 mole I2 at that temperature. Value Kc is 50.5 with equilibrium concentrations. I'm always going to probably start by writing out my equilibrium expression, products over reactants. Okay. And then I'm going to start by doing my ice problem. In this case, remember, we need to look at the concentrations. So I'm given that it's 1.00 moles in a 1 liter flask. So on the plus side, the number of moles is actually the same as the molarity, but keep in mind that might not always be true, and so you're going to need to make sure that you're using the correct units, because ice problems really only work with concentrations. Okay. In this case, it's obvious which way it's going to shift. We've got zero products and we've got non-zero amounts of reactants, so we're going to go ahead and say this is minus x, this is minus x, whoops, sorry, that was a positive sign, a minus x, and this is plus 2x. Remember that 2 comes from the ratio of H2 and I2 consumed to HI produced, right? So this coefficient up here is going to be reflected in my algebraic expression. So the equilibrium concentrations are 1 minus x, 2 minus x, and 2x. Okay, so in this case, we have to fill in our Kc expression. Remember that was 50.5 is going to be equal to 2x squared over 1 minus x, 2 minus x. Okay, so in my first video, I said that sometimes we can avoid using quadratic by determining if x is small compared to starting concentrations. And I look at this here, though, and I say that 50.5 means that this reaction favors products, right? There are more products than reactants at equilibrium. And since I'm starting with reactants and going to products, and I have zero products, that actually means that x is going to be large, okay, compared to those starting concentrations. So I am not allowed to approximate by getting rid of those subtracted terms. I can't use that approximation. What that means is I need to use the quadratic. Again, I recommend Wolfram alpha, or if you have on your calculator a quadratic formula. Part of the reason I want to show you this is I'm going to show you the solution. So I used Wolfram alpha, and I got that x could equal 0.935 molar, or it could equal 2.32 molar. Okay. In these cases, you're going to have to use logic to choose which one is correct. Obviously, x has to be 0.935 molar, because 2.32 would consume more H2 and more I2 than I actually have, and that's not possible. So 0.935 is the only logical choice here. And then I can use that to determine the concentrations of everything at equilibrium. So HI is going to be 2 times that. I2 and H2. I actually did not do the math for these guys, so I'm going to do that really quick. So just 2 minus 0.935 is going to be the value of I2. It's going to be 1.07 molar, and H2 is going to be 1 minus 0.935. So that's going to be 0.065. Okay, let's say that you, however, are in a situation where you can't use the quadratic formula. There is actually another way of imagining this problem that'll still allow us, to use this approximation that we tried to use a second ago. This is an advanced way of doing it. If you are not comfortable with doing it this way, that will be okay for right now, but I would like to explain to you how you would do this. Okay. If you have a large Kc, and you're starting with reactants, wouldn't it be easier to say we were starting with some number of products? If we're starting with some number of products, then this becomes a little bit easier, because then we're going to shift this way. We're going to shift backwards, and that x will be small. in a situation that favors products. What do I mean? Okay. In this case, let's assume that reaction goes to completion to start with. This is kind of step one. All right, what does that mean? That means in this case that H2 will be my limiting reactant. So when I set this up again, my new initial after assuming that the reaction goes to completion is 0 H2 because it was limiting. It is 1 molar I2 because H2 and I2 react in a 1-to-1 ratio. So if I've reacted 1 mole of H2, I've reacted 1 mole of I2, resulting in 1 molar being left over. And I've got 2 molar HI. Okay, because for every 1 mole of H2, I get 2 moles of HI. All right, so those are my new initial things. In this case now, since I have 0 molar H2, the change has to go in this direction. It has to go from products to reactants because I can't react 0 moles of H2. So that means here I have negative 2x, I have plus x, and I have plus x. Okay, so the reaction is now going in the opposite direction. Now, so 3, solve ice problem. Okay, so now in this case I have 50.5 equaling 2 minus 2x squared over x times 1 plus x. Okay, and in this case, looking at this, right, we're not going to be shifting far away from the products because my k is actually large. I expect x in this case to be small. All right, why is x small? Because we're not going to shift very far backwards in the other direction when the products are favored in the overall reaction. All right, so in this case, x is small, so I will get rid of all of the added and subtracted terms of x and rewrite this as 50.5 equals 2 squared over x. Okay, in that case, when I solve for x, I get 0.079 molar. And let's go ahead and just solve them for the concentration of HI in this case. That means the concentration of HI is going to be 1.84 molar. And when I compare that to what I did using Wolfram alpha and the quadratic, I see that I have a very small percent difference. In fact, 1.87 minus 1.84. Right, that's a difference of 0.03. So if I divide that by 1.84, for example, right, I only have like a 2% difference between these two values.